Hello, good afternoon. Check to see the sound's working. Yep. Hope everyone is doing all right. We're through week 3 together, and I hope that if you're finding these videos that they're helpful in any way that we're able to contribute to your virtual and remote learning. Really appreciate your time and attention. And remember to reach out to your coordinators if you're in need of anything, and hopefully we'll be able to provide some support. It's Friday, so we're picking up on statistics. We talked last time about some probability ideas, and in particular we were looking at spinners, and before that we looked at marbles, colored marbles being drawn from a bag. Today we're going to talk about dice. So you could say that this is the third in a series here of probability where we're talking about sort of typical probability environments, or especially theoretical and abstract probability, tools or props, like what we use to think about probability. This is a major one. Dice is a major one because they're not only used in a lot of like gaming environments, but they're actually were crafted somewhat similar to the spinner in order to do these types of things, in order to illustrate randomness as best we could. And so what we're going to deal with at first here is six-sided. So you may be familiar, but you may not. It's a cube with 6 faces, as all cubes have. And each face has a certain number of dots on it, ranging from 1 to 6. Okay, so that's what they look like. You've probably rolled one at some point in your life, or multiple. So they have these outcomes kind of pre-made, and they're constructed when they're fair dice to be theoretical probabilities, that the probability of getting a 1 is equal to the probability of getting a 2, 3, 4, 5, or 6. Well, I should state that differently. The probability of getting any side face is equally likely, and it's 1 over the number of faces, 1/6. So a cube being kind of a perfect shape for this. You might have also seen maybe a 4-sided dice, which looks like a pyramid with a triangular base. You might have seen 12-sided or 8-sided dice, which is a diamond, or even 20-sided dice. This same idea kind of also fits for coin flipping, which is like you have 2 faces, each are equally likely, 1/2 each. This 6-sided dice, 6 faces, each 1/6 chance. Okay. So let's ask a couple simple questions, like what is the probability that the outcome of a single roll is greater than 3? Well, that's the probability of a 4 or 5 or a 6. Those are mutually exclusive, so 1/6 plus 1/6 plus 1/6. 1/2. Makes sense. What's the probability of an even? Also 1/2. Probability of an odd? Also 1/2. Probability less than 6, 5/6, so on, so on, so on. So we can do a lot of different things with the 6-sided dice. That is useful. Let's think about a compound probability, an and probability. The probability that x is greater than 3 and even. Well, think about our sample space, 1, 2, 3, 4, 5, or 6. Probabilities there, 4 and 6. Now let that be contrasted with the probability that x is even given x is greater than 3. So you've rolled the dice, you know that it's greater than 3. What is the probability that it's even? Well, if you know that it's greater than 3, you're only thinking about these 3 dice. You know that the outcome is greater than 3. And the likelihood there of it being even is 2 out of 3. So there is a difference here between compound probability and conditional probability. Stated another way, what is the probability that the outcome is even given the outcome is either 4, 5, or 6, all equally likely? So we'll come back to that, but there is a formula here that we want to think about, which is that the probability that x is even given x is greater than 3 is equal to the probability x greater than 3 and even over the probability x greater than 3. In other words, we can think about conditional probabilities by limiting our denominator. So we're no longer looking at all possible outcomes, right? We're no longer looking at all outcomes 1, 2, 3, 4, 5, 6. We're only looking at outcomes 4, 5, 6, because that is the likelihood of those outcomes happening 1/2 of the time. But we know we're in that half. We know we're in that half. Let's take a look at another one. The probability of getting less than 4 given that it's odd. Another way of looking at this. Let's look at the two outcomes as event diagrams. What are the things that are both odd and less than 4? Well, 1 and 3. What's odd but not less than 4? 5. What's less than 4 but not odd? 2, which is even. So you can kind of see, like, in general, what types of outcomes are we talking about? We also have 4 and 6, which are outside of our event space here for either. So if we know x is odd, we know we're in this circle, right, of outcomes. Now we know we're in there, so there are only 3 possibilities, each are equally likely. Therefore, if we're now asking among 1, 3, and 5, what are the odds that what is the probability that we're below 4? Well, 2/3. And looking at the formula here, it's the probability that we're less than 4 and odd, which is 2/6 or 1/3, over the probability that we're odd, which is 1/2. So conditional probability is typically a difficult concept for people, but I don't think that it has to be. It's not technically, from a technical standpoint, particularly difficult, as long as we recognize what the symbols look like and how the statements are read. I think if we can read the statement correctly, that goes a long way. So for example, what I'm talking about is this type of statement. The probability that the outcome on a dice is less than 4, a 6-sided dice, given that the outcome on that 6-sided dice is odd. So we know that it's odd, we've rolled it, we know that it's odd, 1, 3, or 5. What then is the odds, the probability that it's less than 4, 2 out of 3? Let me reset real quick. All right. Now, what about rolling 2 6-sided dice? Sometimes you'll see the word die for a singular. I use dice in both cases. So we could ask, you imagine this, right? So you see the 6-sided dice, it's a cube, 6 faces. Each face has a certain number of dots, 1, 2, 3, 4, 5, or 6 dots. One face has each of those, right? So there are 6 faces, they take on these outcomes. What if we have 2 of them and we roll 2 of them? So there's a lot of questions we can ask. One question we can ask, or a very common set of questions, is about the sum. So we could, for example, ask, what is the probability that sum is, let's say, 4? Well, we can think about the 2 possible ways to get there, right? Either have a 1 and a 3, or 2 and 2. But it's not quite that simple, right? So this is, of course, the sample space, but we have to think about the probabilities here. There are actually 2 ways to get a 1 and a 3. You'd have a 1 on dice A, and a 3 on dice B, or vice versa. How do we want to visualize this? And this is another useful way. We've done tree diagrams a little bit. This is a useful way too, is to create a chart of outcome correspondences. So let me do that. See if I can give myself enough space. Let me roll. Here we go. It's difficult to do straight lines freehand on this because it's not down on the table. It's upright. I want to give myself enough space to think about these outcomes and their sums. Okay, Let's go clean it up. Oops. Okay. So these are outcomes of, like, say, dice 1 or dice A and dice B. Oops. And in the boxes, we're crossing the two outcomes. So we're saying, like, this top left box right here is a 1 on dice A and a 1 on dice B. So the sum in green is 2. And we can now think of it, fill it out pretty quickly here. A 2 on dice A, a 3 on dice A, a 4 on dice A, a 5 on dice A, a 6 on dice A. And let's even pick, like, some random boxes that are left to just make sure we know what we're doing. Like, let's think about this box. That's got to be a 7 because it's a 5 on dice B and a 2 on dice A. The sum there, 2 plus 5 is 7. Think about, like, this box here must be 11 because it's a 6 and a 5. This must be 10 because it's a 4 and a 6, and so on. So it's useful to fill it out like this, I think. Hopefully you can see the pattern. That's why I'm not actually doing sums. I know what the pattern is here. As I change rows or columns, one over to the right or one down, I'm adding 1 from the previous because that's what's happening. One dice is getting larger. So that's what the outcome for sums of 2 6-sided dice being rolled looks like. Now, the benefit of this, we're drawing this out. We can now calculate probabilities very easily, right? First thing we need to do is recognize there are 36 different outcomes, right? And here we're talking about, meaning if we've labeled the dice, say 1 is red and 1 is blue, even colored like that, you know, you could have a 1 and a 1, you could have a 2 and a 1, but if you have 2 and a 1, a 2 on the red and 1 in blue, a 2 on the blue and 1 on the red is different in terms of the outcome when considered this way, and that's useful. Because we don't want to only consider that there are only the outcomes 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and mistakenly say that they're equally likely because they are not. So we can answer questions from this pretty well. Shrink this down. You can see the probability that the sum is a 4. It's going to be 3 possible ways to get a 4. 1 and 3 2 ways, right there, right there. 2 and 2 1 way right in the middle there. So this is going to be 3 out of 36, which is 1/12. Probability that the sum is odd. Counting is a principle in probability. If you can count the number of outcomes and then count the number of events that are successes, or outcomes that are successes for your event, you can put 1 as the numerator, 1 as the denominator in the right spots here. So we know there are 36 possible outcomes. Let's count the ways to get an odd. Well, there are 2 3s, 4 5s, so that's 6. 6 7s for 12. 4 9s for 16. 2 11s for 18. Okay. What's the probability that the sum is greater than 8? We're talking about sums of 2 6-sided dice. So it's out of 36. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the chart really organizes it well for us in this case. Because we went left to right, top to bottom, 1, 2, 3, 4, 5, 6, we get greater sums as we move right and down. probability that the sum is a prime number. Apologize for that, my dog barked. The joys of being at home, huh? Probability that the sum is prime. We don't want to lose track of the other mathematical concepts that could come into play. So we have to remember what our prime numbers are. They're numbers divisible by only themselves and 1. So outcomes like 2, 3, 5, 7, and 11. None of the even numbers besides 2 work because they're all divisible by 2, and 9 doesn't work because it's divisible by 3. So this is 1, 2, 3, 4, 5, 6, 12, 14 out of 36, which simplifies, it looks like, to 7 out of 18. Now, let's take a look. Actually, I'll erase these 3 that we've just done to give ourselves a little bit of space. We're going to do some conditionals on this sum. So first question, the probability that sum is even given that one dice is 4. Now we have the formula that we could look at. Okay, the formula is useful, but you still have to count properly. So for example, one of the issues here is either dice could be 4. So we need to really be paying attention to what outcomes we're being constrained to looking at based on the given. We are given that one of the dice is a 4, not that the dice A or dice B specifically are 4s, but either one could be 4s. So really quick, I'll highlight the outcomes we care about. It's only those 11 outcomes where one of the dice is a 4. And now we need to count out of those 11 outcomes how many have sum of even. 1, 2, 3, 4, 5. Take back the highlighting if I can. Yes, okay. Now let's reverse the order. Probability one dice is 4, given the sum is even. Well, now what outcomes are we talking about? Let me highlight them. We're talking about this, these, $18 outcomes. 18 outcomes. How many of those outcomes is there a 4 on one of the dice? Not exactly 1, but could be both 4. Well, I count 1, 2, 3, 4, 5. 5 out of 18. So do you see what's happening here with these conditional probabilities? It's a complicated but pretty nuanced and actually quite powerful and fascinating tool for us. We're able to, instead of having to look at, say, the larger picture, if we know some information here, the givens, what come after these horizontal splits here, those are going to indicate for us what is about to be given. So we read, like, say, the first one, what is the probability that the sum is even given one dice is 4? And for the second one, what is the probability one dice is 4 given that the sum is even? can see the power of these types of tools. We are able to constrain or restrict our view to only those outcomes which already fulfill the given. So it changes the probability in a lot of cases, usually lowering the probability, but not always. But in the problems we see, I think that's fairly common. Let's look at one other one to explore and leave the day and week on. Probability that the sum is greater than 7, given that one dice is a 1. And this is something you should visualize or write out when you're working on these problems, is this outcome table or some representation of the outcomes. So that when it's possible, especially when there are a small number of outcomes, if one of the dice is 1, we're talking about these. So then what is the probability that the sum is greater than 7? 0. So hopefully this is making good sense. I highly suggest you draw one of these tables out for yourselves, or if you're at home and you have a board game or access to a couple of 6-sided dice, take them out and look at them and study them. Now notice that what we're doing, we're not talking in these cases about experimental probabilities. So we're not rolling 2 dice and looking at them and trying to make any inferences. What we're saying is that we know the qualities of these 2 dice. They are 6-sided. We know how their faces are numbered. We know each face is equally likely. So we can predict accurately the likelihood of outcomes. That doesn't mean, for example, to predict in particular any outcome or any 2 outcomes. We don't roll the 2 dice and say, oh, okay, we got a 3, that means 3 is more likely or something like that. No, it's still going to be 2 out of 36 times. To get a 3, you just happen to get 2 out of those 36 times. So it's a very useful thing to remember when we talk about theoretical probabilities, especially when it comes to very small likelihood things, that when those happen in the world, it doesn't necessarily mean that the likelihood is higher than we thought. It could, but for things like dice and cards and things that are constructed to be fair in these mathematical settings, we're able to say that rare outcomes happen exactly as rare as they're calculated to be. So thanks for stopping by. I'll see you next week. We'll talk more about probability, maybe deck of cards. Take care. Have a good weekend.